Welcome to S1. Today we're looking at Chapter 6, Discrete Random Variables. Now, just before we get started, if you're yet to subscribe, please hit that subscribe button as you'll really help me out. Thank you. Now, let's get started. So first, let's talk about the words. So discrete is from discrete data. So it can only take specific values, usually whole values, but it could be half values as well and so on. Okay, but it takes specific values, and as I said, usually whole values. Random variable, well, a random variable is just a variable whose value depends on the outcome of a random event. These are usually written as uppercase letters, for example, like an X or a Y, where a particular value is usually written as like a lowercase, so like a lowercase x or a lowercase y. Now you often see this written down, and it just means the probability that the random variable x takes a particular value x. Let's look at an example. Now, in this example, I've just given the information. I haven't actually written down what we're trying to find, okay? But it's just quite important to look at everything. So we've got 3 coins. So if I toss in 3 coins, all my possible outcomes are I can have 3 heads, I can have 2 heads and a tail, but there's 3 different combinations of that. I could have a head and 2 tails. Again, there's 3 different combinations of that. And finally, 3 tails. So you can see here in total I got 1, 2, 3, 4, 5, 6, 7, 8 possible outcomes. Now, a probability distribution describes the probability of any outcome in the sample space. And you have kind of 2 ways of doing it, either a table, sometimes a diagram, or a function. Okay, now I'm not going to put a diagram down, like a little graph or anything like that, because it's not very often that you'll be asked to do that. But a table and a function, these are 2 that are common. So we're looking at the number of heads that appear. So if I throw 3 coins, I could have 0 heads appear, 1 head appear, 2 heads appear, or 3 heads appear. So this one is number of heads, and it's little y, okay, because we've got the random variable y there. And then the probability of one of these happening, which is written like that, is just now, all I need to do is think of, right, 0 heads, that's just when it's 3 tails, and that's 1 out of 8. 1 head is here, so we got 1, 2, 3 outcomes. 2 heads is also 3 outcomes, and 3 heads is 1 outcome. So those are my probabilities there of each of these events happening. So this is in terms of a table. Now, in terms of a probability function, it's written like this. So again, we're looking at probability y equals little y, and then I want kind of a bracket almost. And at this point, I need to look into my table. So look at my scenarios. I've got 1/8, 3/8, 3/8, 1/8. So I've only got 2 different probabilities, 1/8 and 3/8. So 1/8 and 3/8. And I pop those into my function. The next thing is to set my values. So in this case, sometimes you can put this as a range, but in this case, 1/8 can only take the values of 0 or 3. and 3/8 takes the values of 1 or 2. So these are the possible values that the random variable can take that will give me this as a probability. Now, in some questions, definitely in S2, when you get to S2 next year, but in some questions then you'll also have the probability of 0, which is written as otherwise. Okay, all that's saying is, here you can see we've got 0, 1, 2, 3. Any other value of y would return a probability of 0. Okay, that's what that means, which is kind of obvious in this case because we've only got 3 coins. So, you know, in this particular case, you probably didn't need it, but I've popped it in there anyway. Okay, so it just means that any other value of y would return a probability of 0. And it kind of goes without saying, but the sum of the probabilities of all outcomes of an event must add to 1. So you can see here 3/8 plus 3/8 is 6/8, 7/8, 8/8, which is a total of 1. That should be the case for all of these random variables. 3 straightforward questions for you to have a go at here, answers to follow. Now, next thing we need to look at is cumulative distribution function for a discrete random variable. So this is when we're looking at the probability of a value and all the values below that. Okay, and what we use is we use this letter as a capital F. So capital F of x. This just means the probability when x is less than or equal to that small x. So essentially before we would actually have been using a small f for a function, and that was when x equaled x, large X equals small x, just think of it like that. Okay, now with capital F, this means cumulative. So it's like a total probability up to this value. So if this value is 5, it's the probability of all the values of x up to and including 5. And it's written like this, capital F of x. So if I use our previous example, we were looking at the distribution, well, we had 3 coins, didn't we, landing on heads. So if I wanted to think of cumulative, all I need to do is add an extra row. And we will put in our capital F of x, but in this case we were using y, so it'll be capital F of y. And because it's cumulative, what it means is the first one is the probability of less than or equal to x, or sorry, less than or equal to y, which would be just this 0. So that's going to be 1/8. However, the next line is the probability of less than or equal to 1. So if it's less than or equal to 1, it could be a 1 or a 0. So it's 1/8 plus 3/8, which is 4/8. and I will simplify these in a moment. The next one now is less than or equal to 2, so it's 2, 1 and 0. So adding these three together or adding this one to the previous one, which will give me 7/8. And then less than or equal to 3 is going to have a total of 8/8 or 1. So simplifying these, this one should just be 1, and my 4/8 can be written as a half. And that there is my cumulative distribution function for this discrete random variable. What you'll always notice is that this final value will always be 1, because if it's the probability of all your possible outcomes, it's got a total 1. So you know that this will always be 1, and that will always help you out. Now, to throw you off, sometimes they might ask you for something like this, which is the cumulative distribution, or the cumulative value up to and including 2.6. So like this, for a discrete random variable, it can't obviously take a decimal, can't be between 2 and 3, so it's actually going to be, if this is the probability when y is less than or equal to 2.6, then it's obviously got to be when y is less than 2, or less than or equal to 2, I should say, because it can't be any other value, it has to be a whole value. And then in this case, I can look up to 7/8, and that would be my answer. Okay, so hopefully that makes sense. Okay, so cumulative function is just essentially like a running total. You're adding your new probability to the previous one until you get essentially to your 1. So it's just adding up the previous ones. Okay, now in some questions you might be given the cumulative function and need to work your way back to this function, and that would be straightforward. A half take away an 1/8 would give me my 3/8. 7/8 take away a half will give me my 3/8. 1 take away 7/8 will give me my 1/8. Because if I just wanted to find, say, the probability when y equals 3, it's the same as the cumulative up to and including 3, so less than or equal to 3, minus less than or equal to 2. Okay, so in this kind of case, you can always go backwards as well if you've given the cumulative function rather than the probability distribution function. Okay, so this is a probability distribution function, PDF, and this is the cumulative distribution function, CDF. Okay, small f, capital F. Now we do this because this is, if you think about it, when it's the probability that x is less than or equal to 4 minus the probability of x is less than or equal to 3. So this is 1, 2, 3, this is 1, 2, 3, 4. So if you take away the 3's, you're just left with that 4. Now for the second one, we remember that f of 2 minus f of 1 is what's going to give us the probability when x equals 2. So f of 2 is going to be 3 over 6, but f of 1 is 2 over 6. So that leaves me with 1 over 6 here. Then for when x equals 3, we're looking at f of 3 minus f of 2. So f of 3 is 4 over 6, f of 2 is 3 over 6, which is going to give me 1 over 6, and so on. And then all that's left is to simplify my 2/6 fraction as 1 over 3. Now, the next things for us to find are our expected values and our variance of our discrete random variable. Now, the expected value is often written like this, e of x, but sometimes you'll see it as mu, okay? It means the mean. Okay, so e of x, expected value, mu, or the mean. And as you get more and more observations, you'll get closer to this expected value. As it's the mean, it is a theoretical value in essence. And to find it, it's just the sum of x times p, your probability. So all you do is when you have a table, is just x times p, x times p, x times p for all your values, and then add them up. So let's have a look with an example. So I've taken this from one of the other previous questions. So if I want to find the expected value, okay, I take my x and I multiply it by my probability. So I get 1 times 0.1. And then I take my x and multiply it by my probability. So that's 2 times 0.1 plus, I get 3 times 0.15 plus 4 times 0.25 plus 5 times 0.3 and 6 times 0.1. And all I need to do then is total this up. And this is then the expected value of this distribution, okay, which is essentially its mean score, or its mean value. Now, we also need to be able to find the variance. Now, the variance is often written as VAR for variance of x, and sometimes it's used with our variance symbol, which is the standard deviation symbol squared. Now, the variance of x is actually e of x minus e of x squared, which as it stands is a little bit unhelpful and not useful. Now this has an equivalent form, which is e of x squared minus e of x squared, like so. Now, I've already shown you how to find e of x, this part. Let's look at how we find e of x squared. So to find e of x squared, all we need to do is the sum of x squared times the probability. So it is the same as what you can see up here, except for you square the x first. So for our case, in this example, we'd have 1 squared times 0.1 plus 2 squared times 0.1 plus 3 squared times 0.1 and so on. And that you can see then gives you 16.95. So in our example, and sorry I've just put these in boxes just to stand out, but in our example our e of x squared, so now we've got e of x is 3.85, e of x squared is 16.95. So my variance of x is 16.95 minus 3.85 squared. And here we get 2.1275 or 2.13 to 3 significant figures there. Okay, and that's my variance. And you know, it's quite easy to do. Okay, sometimes in some questions you might actually need to find e of x squared when you know the expected value and the variance. So you might need to use this formula kind of rearranged to find this. So you don't always need to find e of x squared from a table. Sometimes you might be given the variance and the expected value, and you can use this formula to find e of x squared. So what I'll do now is I'll pop a few questions up to give you a little bit of practice on the expected value and the variance of x. Answers will follow. Now, going with the expected value and the variance of a function, there's some additional rules you need to learn, which can also link to coding. Okay, and these are quite straightforward. So, e of ax plus b is a times e of x plus b. And for the variance, it's a little bit different, and this is because variance isn't affected by when you add or subtract a value to it. So for the variance, it's a squared variance of x. Okay, it's squared. You don't really need to know why, but it's squared because the variance is worked out by the distances squared. Okay, to get positive values. So this is squared variance of x, and plus or minus b makes no difference because that just moves, it translates the line up or down. It doesn't affect its variance from a line. So that's what you kind of need to know, these two. And going with this, if I had two, so like the expected mean of, or expected value of x and y, the random variables x and y, is the same as e of x plus e of y. I've put this over on this side because it's not as, I wouldn't say it's not as useful, it just comes up far less often. whereas these two will appear pretty much in every exam paper. They'll also appear later in next year in S2. So let's do an example and then a few questions with this. Now, for this type of question, for the first part, we want to work out the probability of y, where y is 2x plus 1. So the first thing, we're going to basically rewrite this table, which means that this is going to become y, this is basically y there, and 2x plus 1, so 2 1s plus 1 is 3. 2 2s are 4 plus 1 is 5. 2 3s are 6 plus 1 is 7. 2 4s are 8 plus 1 is 9. We've got 11 and 13 at the end. And the probabilities themselves, well, they will stay the same, because that's the same probability at that point. It's just replacing an x with a y. Because essentially, the probability when x equals 1 is the same as when the probability when y equals 3. That's the idea behind it. Okay? There's no, we're just changing how x is being written in terms of y. It's like coding. Okay, so that's part A done. Part B, so e of y, I can do this the way we did it before, so it's the sum of y times the probability when y equals y. So that should be a capital Y there. So that's my 3 times 0.1 plus 5 times 0.1 plus, and so on, all the way up to 13 times 0.1. And that gives me 8.7. However, this is an example that we did earlier. And in the example earlier, e of x was equal to 3.85. So if I think of this the way we've just been looking at it, e of y is e of, and then y is 2x plus 1. So that's 2 times e of x plus 1. So 2 times 3.85 plus 1, and we get our 8.7. And that is essentially there what I was doing in part C. Okay, just showing you how this method works. Obviously I didn't need to find e of x again because we already had it. Now, finally, you may come across a uniform distribution. This is when the outcome, the probability from an experiment, etc., is exactly the same. Okay, an example of this would be, when you roll a dice, the probability of getting each number on a dice, as long as it's a fair dice, will be 1 over 6. And that's the same probability for all the numbers. Now, when you have a uniform distribution, so a discrete uniform distribution, then there's some additional ways of finding your expected value and your variance that makes it a lot easier. So the expected value is simply n plus 1 over 2, and the variance is n plus 1 multiplied by n minus 1 over 12. Now remembering these will just save you a lot of time. Okay, you could still work out the values the same way as we did previously, but spotting that as a uniform distribution and remembering these two formulae will save you a lot of time in an exam. So let's look at a quick example. So in this example we have 7 similar balls placed in a bag, have numbers 1 to 7 written on them, and a ball is drawn out at random. Now, since these balls are the same and they're in a bag, the probability will be the same. It'll be 1/7 for each of them. Now, it's not a requirement to do this distribution as a table here. I'm just doing it so that I can show you. Now, part A, what I'm going to do is I'm going to do this both ways. So the long way would be how we've done it before. So that's 1 times 1/7 plus 2 times 1/7 and so on. Now the easier way, because this is a uniform distribution, discrete uniform distribution, is n plus 1 over 2. And n is going to be 7. 1, 2, 3, 4, 5, 6, 7. So 7 plus 1 over 2, so that's 8 divided by 2, which is 4. And you can see that's the same answer. Okay, but you can see that working out wise and amount of time taken, it's a lot quicker. Now, let's have a look at the variance. So first what I'm going to do is I'm going to do this the long way, just to show you. Which means I first need to work out E of x squared. So therefore, the variance of x is going to be 20 minus 4 squared, because E of x squared minus E of x squared. So 20 minus 16 is going to be 4. Now let's look at it doing it the faster way. Since it's a uniform distribution, this is n plus 1 times n minus 1 over 12. So we've got 7 plus 1, 7 minus 1 over 12. So it's 8 multiplied by 6, which is 48, divided by 12 is 4. Now you can see that this is obviously way quicker. I didn't need to find E of x squared to be able to find the variance within a uniform or discrete uniform distribution. Okay, so using these two formulae, hopefully you can see how much quicker and easier it is to work out your expected value and your variance. Now, I'll give you a couple of questions to try, and as always, pop the answers after them. Now for part B, we need to know the standard deviation. So we currently know that the variance is 35 over 12. So the standard deviation is going to be the square root of that. which is approximately 1.708 to 3 decimal places. Now, if it's within 1 standard deviation of the mean, then that means we want the mean plus 1 standard deviation and the mean minus 1 standard deviation. And we know the mean here is 3.5. Okay? So mean plus 1 standard deviation is 3.5 plus my 1.708. And that will give me 5.208. And then the mean minus 1 standard deviation is 1.792. Now both of these are to 3 decimal places, although on a question like this, 1 decimal place or 2 decimal, it doesn't really matter because it's discrete data, so I'm going to have to round my values off. So since we're finding probability, and we're finding probability that it's between these 2 values, so we'll find the probability that x is between my 1.792 and 5.208. Now, since this is discrete data, that would mean that we're looking at between 2 and 5, and including those values. Okay, because this whole value will be within this range, and this whole value is at the other limit of the range, within this range. Now, probability of rolling a 2 plus the probability of rolling a 3, 4, or 5. So it's quite obvious, it's just 1 6 plus 1 6 plus 1 6 plus 1 6. So 4 over 6, or 2/3. Final question is quite simple. The expected value is 4.5, which means that you would be expected to make 4.5 cents on average, over a large number of spins, but it's costing you 5 cents to play. So this expected value is lower than the cost to play, therefore you would expect it to make a loss over a large number of spins. Hopefully you found this video useful. If you did, feel free to hit the like. If you want to ask any questions, comment down below. And if you are new to the channel or you haven't subscribed yet, please consider hitting that subscribe button for me. Thank you.